We are live. So welcome everyone and welcome to this week's Coding in Public. I'm Theo, Quix's community manager here, and really excited to be joined by Javi, who is my colleague, but also the senior data scientist here at Quix. So hey Javi.
Hi, how are you, Theo?
Right.
Should I just go ahead and start? Can you see my screen over there?
I can see your screen. I was just going to say, like, if people are watching at home, like wherever you are, like feel free to comment on the YouTube video. You can ask questions, you can say hi, you can say where you're calling from, any of the above. And maybe even if you want to like play along at home, Javi's going to show some of the platform. You can do that by just going on to quix.ai/sign up, and that will bring you there. But that's it on admin. So Javi, I'll pass it back over to you.
Great. So, that's me. I'm Javier Blanco, and today I'm going to be talking and playing with a data science project, but specifically, we are going to see how streaming can play a role in a data science project, where it can be beneficial and where maybe we don't need it. For this example, I'm going to be using the New York City bikes prediction as our data science purpose in this project. In terms of contents, we're going to go through this session over this one. So first, I'm going to tell you a bit more of what I'm trying to build. Then we are going to see the differences between streaming versus batch. We will see how we are defining the phases of this data science project, and then go through them in detail. So first, the goal today is not specifically to talk about New York City bikes prediction, but how streaming can play a role in a data science project and where it can be beneficial. So we will be focusing on the differences between batch processing approaches and streaming processing approaches. And then we will try to build different predictions for New York City bikes availability. We'll play with different time frames. So we'll predict the availability in 5 minutes from now, 1 hour from now, and 1 day from now. We are going to keep it within those time frames. We are not going to be doing here more strategic type analysis like above 1 day ahead predictions. The idea here is that we are going to be performing predictions on data that has the most value when it is produced. Like if we're interested in creating a 5 minute from now prediction, maybe to send it to our users app for their route calculations, the information that we have right now is the most valuable. If we act on it a minute later, we will have the information will decrease in its value. So we are interested here in that type of situation where the value of our data will decrease heavily with the time that it takes us to act on it. That's why we are focusing on these prediction timeframes. Great, now that we know what we are going to be doing today, let's talk a bit more about streaming and let's compare it with batch. So a nice way to put this and a traditional way to present the difference between these two approaches is to show data being created as that river that you see flowing over there. So this is our data flowing. Now, under a batch approach, what you do is you store that data somewhere and then load that batch of data onto your processing system, maybe your data lake. So you wait to have that bucket full of water, and then you throw the water to your data lake. That's how we work with batch. With the streaming though, we are building pipes. So we consume the data piece by piece, and that means that we can process it or modify it piece by piece, hence reacting pretty much in real time. Let's see these differences with another example. imagine we have this set of data over here, these 5 points of data. Under the batch processing approach, we first load that data into our system, and then we perform an aggregation on that data to then push it to wherever we need to consume it. Under the stream processing approach, as soon as we get this piece of data, we perform the operation. So you see, we are saving ourselves some middle steps and some computing resources. For those of you who are not that familiar with streaming, I'm going to introduce now the very basics of a streaming architecture. And the number one is topics, Kafka topics. So these are pipes. This is the infrastructure where we share our data. Then on the one side of the topic, we are going to have a publisher. This is a party that will produce the data and send it to the topic, just like you see in there. So, but this is not a database. That data is not going to be persisted there forever. It becomes available for some time, then it's not there anymore. Then at the other side, we are going to have a subscriber. This is a party that is listening to the topic, subscribing to the data, and consuming it as it becomes available. So we have topics, we have a sub and pub pattern, pub and sub. The other great thing about streaming architectures is that they are asynchronous. So it doesn't matter how many producers or subscribers there are, it works. Or it doesn't matter at which rate the writing or the listening is happening, there are buffering and queuing systems that make this work. Great. So now that we have some idea about the difference between streaming and batch, I'm gonna go back to data science and talk about the traditional phases in a data science project. And there is this quite viral post from Andy Scherpenberg, who you may have seen already. Let's see, the loads. It's basically around how any data science project is seen as somehow gathering the data, then doing something with it, and then actually gathering value. So putting into production that machine learning model or whatever processing you have developed in there. The post goes around how each of those big stages actually compose many, many little phases and how it is hard to develop properly each of those. But the idea here is that, yeah, I quite like that structuring. Just get the data in, find what is interesting in the data, and then actually get us some money with those findings. So put your model into production. So we are going to see our problem in those three different phases. We are going to focus on data ingestion, model training, and MLOps. And my idea today is to actually focus on how streaming can play a role in each of those phases. Spoiler alert, it is really good for data ingestion. It is amazing for your MLOps, for putting your machine learning model into production. And then it's not something you will use for your model training. For that, you need a big batch of data. However, the real-time availability of your data may influence the way you are training your model. So we will talk about that as well. Yeah, so let's focus on data ingestion as the first of those phases. Again, let's recap on the problem we are trying to solve. We are going to be predicting the bikes availability in New York for some different timeframes. Now, for the data ingestion, the first thing that I'm going to try to do is actually be able to gather data from New York bikes. In this data ingestion phase, again, somewhere where we can compare batch and streaming. We can see how maybe the New York bikes company treat this data. If they're using batch, maybe they have a system to store bikes data, another to store data coming from their apps, and then there will be some jobs running periodically, maybe once a day or maybe once a minute, it doesn't matter, but it will be periodically pushing that data, those batches of data into a big data lake where they could then perform analysis or react to that data. This is the batch way to do it. The streaming way to do it is to react to the data as soon as it is produced. So here we see the topics we were referring to. As soon as we have new bikes data, that produces an event, and any system or any processing can be reacting to that. Good. I'm going to try to create now a streaming ingestion system. Obviously, I don't work for the New York Bikes company, so I don't have straight access to their systems. That would be ideal because it would be the way to connect so that we had an event as soon as new data was produced. But we are going to use a proxy here. We are going to build an API system that will be through a loop. It will be doing API requests to the open New York Bikes API so that we get new data coming in. This will be as close as if we had the system connected to the real thing. And for that, I'm going to go to our platform in Quix because this is the easiest way to build this type of service on top of streaming architectures. Let me show you what I have pre-built in here. As you see, I have some bikes topic created, and I have some New York Bikes prediction topic created. Let's see what is going on through each of those. Here in the source is what I have created, the project that I was just explaining. So you see we have here basically an API request that brings the data into some data frame, and then we push that data to a topic. But just for you to see what I'm doing, I'm going to open a collab. That one, sandbox will do. So I will open some new cells over here. I'm going to import requests. And I'm going to go ahead and copy these. Here. Oh, yeah, need to import data time and a bunch of things. Yeah, I actually going to use whatever we're importing here. That way, I won't be forgetting anything. Yeah, this will do. Good. So that seems to have worked. That means I can inspect what's going on over there. Like I can see what type of JSON response we have in there. I'm going to inspect the keys. We seem to have data, last updated TTL. Yeah, it seems we want to check the data. So let's see what we have in there. Sorry. Stations. As you see there, we have some piece of data for each station. For each station, we seem to have the number of bikes available, disabled, dogs available, dogs disabled, and e-bikes available. So what I'm doing here is I'm iterating over those, over that JSON. And for each station, I'm saving the ID, the timestamp in which we are doing this query. I'm saving the bikes, dogs, e-bikes, and I'm also saving the total bikes, which is just an addition of the normal bikes and e-bikes, right? With that, we have DFI, which we can see over here. Good. And that DFI is obviously for the latest station. So whatever station was the latest in that loop, but it gives us an idea of how that data frame is building. Now, if we go back to my code in Quix, the next thing that we are doing with that DFI is I'm opening a new stream within my topic. And to introduce you the concept of a stream, I'm gonna add a new slide over here. So use this template. So a topic, as we have been discussing it, is the infrastructure where the data is going through, the events are going through. So we have a new piece of data that is written into the topic, and that is there available for someone to consume it. However, when the data increases and we want a way to parallelize these, we can use streams. So a good metaphor will be a highway. A highway, the highway is the road, but then you have lines to control and distribute the traffic. So the same idea applies here. We are going to have different streams within our topic to distribute the load. Now, those different streams, we can have different criteria to divide the data into those. In this case, it seems pretty convenient to actually use the stations as the criteria to divide the load. So each bike station can represent a different stream. And potentially, we can also have another stream where we have the aggregated data of all the different bikes stations. And that's good. And that's what I'm trying to do there within my code. So here I'm using Quix streaming library, the SDK, to create a new stream within that topic. So within the output topic, I'm creating a new stream whose name is New York Bikes, state ID, and now I just parse the station ID, right? That will create that new stream ID, that new stream within that topic. And once that is created, I just write the data. So the type of data that we saw in there, that is a normal data frame, you can just pass it to a stream in Quix, and that will send it. But then at the end of the loop, once I have written that into that specific stream, that obviously will be a different one for every loop, what I'm doing here is I'm appending that data frame to a global one that started empty. So this data frame, at the end of the loop of the JSON, will have the data from all the different stations. And all I'm doing here is a sum. I'm adding all the information, aggregating, summing all the information in the different stations to have an overall number of bikes. And that overall number of bikes that is, let's say, in that data frame called df, I'm passing it to a different output stream. This one that I'm creating here with the same method, but with the name all stations New York bikes. Again, all I'm doing is distributing the load of the ingestion. This will allow me to, for instance, plot some specific station. If I wanted, I could create a service that is only listening to this stream ID. I could be listening to all of those and use that distributed load to generate predictions in parallel that are to make the system faster. Or if I'm interested in the whole thing, I have another stream ID in there that has all the bikes data. Great. So this is what we are doing here. And then because this system, I don't want to be querying the system every second. I'm just putting the thing to sleep for 30 seconds. And that's it. This will be running in microservices. This is our thing in Quix. It is a marriage between Kafka and streaming with microservices. So this is running in the cloud and is performing that query that you see. So you see every 30 seconds, it's performing some query, it's giving me some printing here in the logs, but I can interestingly check this data tab, and this shows me the raw data that is being sent to that bikes topic. And as you can see, I can also see how it's been sent in different streams. So I'm going to be filtering by all stations that I already had there. If I click, that is the latest data that we sent. And there we are. You can see here the specific format of the data that I'm sending. Great. You have just seen there how we are sending some data. Nice. So the ingestion system seems to be working. Another thing to note is that in Quix, you have the ability to persist that data, actually, to put it into a database. And we have InfluxDB behind the scenes because it's optimized for time series data, such as we are playing with. So having that persisted is as simple as within topics, choosing to persist that data, which I'm doing. And this has been running for some days now, before today. So I could come here to persisted streams, and I could check my bikes topic. And there you are. These are all the streams within that topic. So we have our data well organized and divided. But if I'm interested in the whole set, the whole amount of bikes in New York, I can now visualize whatever parameter I want. So yeah, I'm gonna go for all. Good. Now, I'm gonna use time beams of, let's say, 5 minutes. And there you see how the bikes availability has evolved over the last week. I'm going to be focusing on total number of bikes. Oh, I took it out, but yeah, I'm going to bring the dogs as well. And we should see how, when the bikes number goes down, the dogs go up, and the opposite, which makes sense, right? Good. So the ingestion system seems working. And let's recap on what streaming has allowed us to do. We have now that topic receiving data in real time as soon as it is produced? Well, we actually have, as you saw, an API request on a loop. But if we were working for the bikes company, we had access to the system that produces the data, that will be sending events to the topic. So we will have that data being produced in real time, and we will be able to consume it and do whatever in real time, including persisting in or putting in the data lake if that's what we wanted. But it will be here for us to act on it in real time. Now, let's talk about the model training. So we are happy that the ingestion has worked. As I said earlier, let's recap. I'm going to be trying to do 3 different models. One will predict the amount of bikes in 5 minutes. The other will predict it in 1 hour. And a third one will predict the amount of bikes in 1 day. This is interesting for us to reflect on the different ways to model this type of problem. Now, being a time series problem, I'm sure many of you know it, but this is probably the Bible for everyone attempting a time series model. And what we are going to be doing here is I'm going to start playing with the simplest predictor that there is. I'm going to show it to you. So the simplest model is called naive, and it is just using the current one. And that's before going into linear models or anything like that. Using a naive model will mean using the latest point of data as your prediction. So I'm coming here. Hey, Thomas, I see you are there.
Hello.
How are you?
I'm great.
Actually, now that I have you here, because probably you are busy, before I go into the model training, Thomas, do you want to talk about the MLOps? I'll do the model training after you do that, but Thomas is our CTO, he's a great data engineer, and he can explain better why the MLOps it's much better with the stream, much robust and faster. Thomas, do you want to go ahead?
Yeah, so I mean, hi everyone. So basically traditionally we have like a 2 type of deployment for ML models. One is API driven, and the newer one, the new kid in the block is streaming. But before we go there, I guess you already already talked about model training, but what I'm going to talk about today is about history training. It's going to be a bit different for online training and different type of applications. But what you probably already used before is the API-driven deployment, where we use the artifact that we created in the training and we deploy it to the microservice, where we expose REST API, which we can call with inputs that then are being basically deserialized and called into the artifact, and the response is then sent back to client. Now, this has some disadvantages. So number one is that it's introducing delay. The REST API call is introducing delay, but also CPU overhead. So the orchestration of the calls are not for free. Now, another problem is, if you can have move a bit, yeah. Another problem is if we get more and more data and more requests from our client, then basically what will happen is that the microservice will get longer and longer to respond to the client, up to the moment where the response is longer than timeout of each request, and client will get timeout, which is not great. This is where basically you have basically your system, it has a downtime. Now, if you have, please move a bit forward, more. a bit more, a bit more. Cool. So you can solve this with scaling your microservices to 2, 3, 4 replicas to address the new amount of data coming in. But you're always going to be basically vulnerable for a spike in data. So if you design your underlying resources for a certain amount of data per minute or per second, and it's suddenly exceeded, you will get again this problem. Now, if we go to the new way of deploying a ML model with the streaming, it looks like this. It's sometimes called pub and sub. So the idea is that you publish requests to input topic in a broker, and then you subscribe to the topic in your microservice, and then you similarly call the artifact as you did in microservice, but then you publish the results to the output topic. Why this is a good idea? Well, first of all, it's very scalable. You can basically scale your processing to multiple replicas. If you can please have a move. Yeah, you can scale your processing to multiple replica. You also get basically subtopics in your topics called partitions that help you to redistribute all the requests horizontally in a cluster to serve more and more requests if needed. And it's very resilient because you basically redistribute your load over different hardware machines in a cluster. So if you have a hardware failure, processing is continuous because the other will take the processing. And also with these technologies, you can set a replica for data as well. So each partition in the topic is sent twice to different machines. So if you have a hardware failure, data are delivered anyway. So hopefully that makes sense. And I'm not sure if you are able to ask any questions.
No, yeah, Thomas, I just want you to explain that because you can do it better. Basically, we've gone through the data ingestion in a data science project. We were going to start with model training, but since you were here, we went ahead and saw the theory of MLOps, of putting that model onto work. So that's great. If you want to stay. Otherwise, I mean, that's great. I can take it from here and go back to model training.
Yeah, so have fun, everyone, and I hope you enjoy the rest.
Bye, Thomas. Thank you.
Bye-bye.
Great. So we've seen now the MLOps bit. Thank you to Thomas. Let's go back to model training. We were about to start up. I was going to say every model training starts with some data. Here's where we will need a certain batch approach. Let's see how I'm doing here to import that data. I'm going to go back to my sandbox that we used earlier. I'm going to go back to my persistent streams that we were visualizing. So let's say I'm now just interested in the bikes because that's what I will build my model on. I'm going to take any aggregation from there. And we can just query that data like this. I'm going to bring that here. Right, and now we are querying the data from InfluxDB in the Quix platform. There we are. This is the latest data available, not just the latest, all the data that has been persisted since that service started. The same thing is what I'm doing here, as this is the same type of query, but I'm using another service that I have been running for some months, actually, and then I'm putting that together with another query here. So I'm putting together an old service with this new one to then do some simple appending. You see there, df historic and df. df is just the same thing that we did here. df historic goes on and does a similar type of query on older data that I had running in another thing. Now, I'm going to want to do some modeling on this data. I'm going to want to predict. And since we don't have any other information here, like weather forecast or any events going on in New York, which will be nice for some other iteration, all we can count on with is the timestamp information. So we can know about the year, the month, day, and so on. So I'm creating those feature variables in case we find them useful. Okay, something from there. I'm gonna rerun this. Okay. Good. And as you can see, the next thing that I'm doing here is I'm using that function over the whole data frame to then actually create the targets. So because we have a point of data every 30 seconds, I'm creating the target using the shift pandas method. So I'm just using a number of rows above the current one. Oh, sorry, below the current one to bring us the target. The number is just easy. So for 5 minutes, because we have 2 points of data per minute, so 2 rows per minute, that times 5 will give us the amount of rows we have to go down. And doing the similar process, we get the target for each of those time frames that we're interested in. Cool. I'm not going to be running that because there seems to be a little issue there, but you can see here what I was doing. Now, I've told you that the current amount of bikes, that is what is called a naive prediction in time series, is actually quite a good predictor. So what I'm doing here is calculating the error of that naive prediction. So bikes minus each of the targets will give me the error for each of the targets that I'm calculating there. And now we are visualizing some of that data. I haven't done it before because we have already done it in the platform, but you can see data for the latest day. You see in black the real amount of bikes. You can see there the amount of, in blue, the amount of bikes in 5 minutes, where you can appreciate very well the offset and so on. Good. That's just some more data. With the y-axis change it, just this gives us a better idea of how, well, it actually doesn't vary that much. The minimum and max stay within certain specific frame. Then the next thing that I'm doing here is I'm performing an split just for our training. And then I use just a simple mean squared error to calculate how good of a prediction the naive model will be. Again, the naive model is just using the latest number of bikes as our prediction for each of the targets. So how good is the current number of bikes to predict the number of bikes in 5 minutes? Well, it is reasonably good. And actually here you see that same data in relative numbers. So here I'm dividing over the mean of each of those targets, and that will give us somewhat of a percentage of mean error. So that shows us how little of an error the naive model does, specifically for the shorter times ahead. Still, for the 1 day ahead is reasonably good. That is because this time series we are trying to model has very strong seasonal effects, both daily and weekly. So current bikes availability now, it tends to be actually a very good predictor for next day. Good. So knowing that the naive model is quite a good one, quite a robust one, how can we improve it? Well, the first thing that I wanted to do here is check, and this is something really similar to the differentiation that an ARIMA model does, or other time series method does, and is I'm going to try to check the patterns that exist within the errors that the naive model produces. And you can see that I can plot the error. This is the blue one is for 5 minutes model. Then we have 1 day, 1 hour ahead model, and 1 day ahead model. And you can see that for the 5 minutes ahead, at the different hours of the day, we have different distributions of error for the naive model. And some pattern seems to emerge over here. Like at this hour, the naive model tends to overestimate, according to the residual, the number of bikes that there are going to be. So maybe there are going to be some modeling that we can do to correct that. And we can see that even stronger with the hour pattern. Sorry, with the 1 hour ahead model for the hour pattern. We could go ahead and do some other testing, like here, not just aggregating by hour, but by hour and minute. And that shows really interesting patterns, some combinations of hours and minutes where the naive prediction doesn't do it that well, and it seems to do it consistently low or up in other cases. And another beautiful pattern here for the 1 hour ahead model. As you see, for the 24-hour ahead one, we don't seem to have that good of a pattern. However, using that, I'm gonna try to do like a better version of the naive model, and I'm going to try to calculate the median for each combination of hour and minute to add that to our naive model to have a better prediction. It's basically doing a group by based on hour minute, and I have added here weekend as well. And as you see, that gives us some mean error that the current naive models have. Then adding those errors to the naive prediction, we have a new, a bit more advanced naive prediction, which is basically using this extra to the bike prediction. That is, if for the 1 hour ahead model, if it's 3 o'clock, it will do the current number of bikes minus 800 or something like that. And that will be our prediction. So using this naive improved model, we see how, especially for the hour ahead, we have quite an increase, right? We improve the prediction capability of the naive model. And that's good. That's good. The next thing that I'm trying here is trying to throw Prophet at it. So probably most of you know Prophet. For those who don't, Prophet is a time series Python and R package by Facebook, by Meta, and they have quite nice theme build inside. What they do is basically component aggregation based on Taylor series, and this type of algorithm is quite good when we have strong seasonalities, just as we have in this problem. So I thought, let's see how good Prophet does it. So I'm installing Prophet there, and because Prophet wants a very specific format, I have to put the time column as TS and the bikes data as Y. I just take out the yearly seasonality because we don't have enough data to learn about yearly seasonalities, but I keep the weekly and daily seasonalities. good. I train that, I save that, do some predictions, and there you can see some visualization. So the data before the red line, I didn't plot it all just to keep it simple, but it was the training. And there was obviously much more training that we see here, much more training than testing. The split was 70-30, if you remember. But what we can see is that the profit prediction is doing reasonably good. With the training data, it's using some nice trend breakpoints to change its trend, speaking very well the daily seasonality. However, over the time in the test region, there must be some specific events that obviously Profen doesn't know about, where it fails quite a lot. And this is where we can be a bit clever about our modeling strategy, because with our streaming ingestion system that we just discussed before, because we are going to have the latest point of data available and updated very often, we could use that together with Prophet to generate a great prediction. This is something very similar to the improved naive model that I did earlier. So because the naive prediction is such a good predictor, and that is because if that day in New York there is a huge rainstorm, or there is an important sports event, or there is a holiday, well, all that information is already contained in the naive prediction. So it's already a pretty good thing to start from. How could we benefit from that and all the seasonal capabilities that Prophet brings us? And that is what I try to do in the next phase. Well, just if you are interested, there you see that Prophet didn't do it that well in that in that modeling strategy. But now we are going to use Prophet not to predict the overall figure of bikes, but to predict the delta of the naive model. So again, this is doing a bit of an ARIMA, or in tree-based models is the same that happens with most of the bagging models, where you have different models, different tree models working in series, each one. Like in XGBoost, you have a first predictor, and then each of the following models will try to work improving the accumulated error by the first and consequent predictions. So doing that same approach, we are going to use Prophet to predict the error that the naive model is leaving. As you can see there, I'm training now 3 different Prophet models, and what I'm passing is now that DF train Prophet. You can see here that that doesn't have as a Y the actual number of bikes, but the error that the naive model had for each row. With that as a target, obviously the error for the 5 minute for the 5 minute Prophet one, and so on for the hour and day. We have now 3 different models, and if I see the results of that, they are quite great. They have improved quite a lot our previously best prediction capability. This is again because we have used the naive predictor to take lots of information on the data, like it has inside that day's weather, or that minute's weather, or whether that time is a commuting time. It will also have whether that is a holiday. There are many, many things, lots of information that the naive predictor is taken by itself. And then for the seasonal trends, both daily and weekly, that thing that Profit does very well, we are using its capability to predict the errors that the naive approach were leaving. Overall, we have something nice. There you see some of the predictions on the test, and all of them are doing pretty well. That's the reason why you don't see some of them behind the black real data. Now, we have done this training. It's just an approach, a different one that I wanted to show here. Doesn't have to be the purpose of this project to discuss whether this is the best approach or not, just one that I use. You also see that I have been saving my Prophet models in some pickle files. There we are. So these serialized objects is what data scientists like me will normally send to a data engineer for them to put those models into production. But I want to show you how with streaming, we can have them not just in a very robust infrastructure like Thomas explained earlier, but also somewhere where a data scientist like me could do it by themselves. So now that we have those models trained, again, we are going to focus on the MLOps. And just like Thomas said, I'm not going to be using an API REST system to call our model. No, what I'm going to be using is this babang subsystem. So we'll have new data coming in through the input topic, and then within this service, it will leave both the model artifacts. In this case, I'm going to have 3, 1 for each model. I'm going to have all the libraries that I need, for instance, Prophet. I'm going to have pandas and everything that I need. And I'm going to have my script that is using the incoming data to generate predictions into some output topic. Again, as Thomas said, this is a great solution, not just because it reacts in as real time as it can be, but also because it escalates very, very well. So if we were deploying these models, well, these models weren't trained to be deployed on each of the stations because they are calculating the overall number in New York. But if they were, we could just connect them to the input topic, and because we created that stream by each stream we created on its station ID information will be the criteria followed to parallelize the load here. We could have a service listening to 10 streams, another one listening to another 10, or whatever. Good. So let's go to Quix and let's put those models into production. And that's happening here in this, well, this Hello World transformation that I created. It's called Hello World because we have here a library where you can find Python samples. I use, the Hello World one, which is just one where you listen to some topic and output to some topic. This is the key where you are doing the transformation that you need. In this case, I use this template to generate the spikes prediction. So again, same template we have just seen, but it has some more stuff going on. So let's see. First, we are importing the pickle files. Well, these are just those that you see there, same ones that I just created in Collab. I have just loaded them here using the upload file. Good. Once we have those models, I have them in this Quix function class when they initialize. That function class is also listening to the input topic. In this case, it's listening to a specific input stream because I'm only interested in the overall amount of bytes. I have this filter here saying, hey, I just want to read the streams that are named like this. Otherwise, I will be listening to all of them, which I don't want in this case. So Over here, I'm going to be having just that stream, but I have that, well, that's some legacy, but I have that just to double check. And then I'm also bringing here to this Quix function 3 different output topics. And this is because I'm not going to output all the streams. I'm not going to output, sorry, all the predictions into the same stream. I'm going to use the great ability that gives me the streams to classify the data differently, to put the real bikes data on one stream, and then we'll have the 5 minutes ahead prediction in another stream, and I'll have the 1 hour ahead prediction in another one, and so on. So this is what I'm doing here. Well, first, listening to the data, and then getting the timestamp of the current data. That will always be. So if I listen to that, put it live. Maybe we have to wait the 30 seconds. But that will show you what type of data I am reacting to. Whilst that is loading, whilst we have, there we are, great. So So now that we can see there how my incoming data looks like, you can see what I'm doing here. First, I'm getting the timestamp, and then I'm calculating the number of bikes using, as you see there, the same parameter name. And then I just throw that away to this output stream, because I want to keep the real number of bikes, not just my predictions. And the real number of bikes has the current timestamp and bikes, so all good. Then I'm going to calculate here the 5 minutes away prediction. The first thing that I do is I calculate the timestamp in 5 minutes. And because the timestamp is in nanoseconds, I just add the amount of nanoseconds needed. So you see in 5 minutes, it will be 5 minutes times 60 seconds times that nanoseconds. And then I use Prophet, the 5 minute away model, to generate the prediction. Remember, this prediction calculates the error that the naive model has. It's not a prediction by itself. So the only thing that Prophet needs is the time data as a pandas data time with that DS column name. So I do that. I'm passing here the timestamp in 5 minutes. And for those of you who have used Prophet, you will know that it returns quite a big data frame with lots of information. But I'm interested just in the prediction, which is that. So I'm saving the prediction, and then I'm adding that to the bikes naive prediction. That is the current number of bikes. With that, I have my prediction for 5 minutes from now. And I'm printing that here, but more importantly, I'm outputting that to this other stream. All these streams are within the same output topic. This stream, the 5 minutes away, will have the same parameters as the previous one, but here in the time, I'm going to pass the timestamp in 5 minutes from now. And for the bikes, it will be the prediction there. And I follow a similar approach for each of the following predictions. I first calculate the actual timestamp for whatever time I need. So this is 1 hour from now. I then use the proper model to do that prediction. That prediction is of the error that the naive predictor will have. So I have to add those. That gives me the overall prediction, and I send that to the proper and specific stream. Again, I do the same with the one-day model, and we are done. And I have had this running for some minutes now. I actually just executed it as we were going to start this presentation. So the model must have been running for 1 hour. So I'm going to click New York Bikes prediction. And whenever the 30 seconds pass, we should see some new data here. We should see four different streams, one for the real bikes data, one for the 5 minutes ahead prediction, 1 hour, and 1 day. Here we are, our 4 streams. And I can check let's see what the model has just done. So the actual number of bikes right now is 22,254. In 5 minutes, the model is predicting that there will be less. In 1 hour, is predicting there will be even less. And 1 day from now, it's also predicting that there will be a bit less. But there you see the different predictions, 3 different predictions for each of the time frames. Now, we could visualize this, for instance, in here, because I am persisting everything going to that bikes prediction topic. That will be persisting the 4 streams that we are interested in. So we have some older streams in there from some previous testings that I was doing, but you can see the ones that we are interested in here. These are the ones we have just created. So if I visualize those, now I'm going to be plotting the bikes. I won't have any aggregation. I'm going to group by stream ID. I'm going to show all. And we see something very interesting here. I told you this started running an hour ago. And we have some data for the day ahead prediction that we won't know how accurate it is up to a day from now. And we have some data here for the other predictors. So independently of the modeling approach, what I wanted to show here is how simple it has been to put those pickle files in an actual architecture that is very robust and also very fast. And that was my idea today. I hope you have seen that both for the data ingestion, both for the ML model deployment, and also when influencing the way you model that data, real-time data is really powerful, and for that we need a streaming. And that was really, Theo, all I wanted to talk about today.
Cool. Well, thanks so much. That was great. And yeah, how do people kind of keep in touch with you if they enjoyed this presentation or have questions?
Well, there are many ways, but the easiest one is if they are trying something and they want some help, we have this live help over here. Both I or anyone in Quix are available there. Well, this is not just a Quix thing, as you know, Theo. There are also events about streaming. There are also industry news. So this is a channel to keep in mind for anyone interested in streaming. So I will say the easiest way is just to join that and ask any question if they have. Also, obviously, we are here to help. So it's not just about answering something there. We can also jump on a call or whatever is needed.
Super. Okay, next week we'll be with Steve, one of our software engineers, who's going to be talking around something else you can do with streaming. So he's going to do a tutorial on how to send alerts to your phone when you have when the Bitcoin price goes up to a certain threshold using Twilio and Coin API. So that's another another way to make the most out of Quix and do some real-time stuff like Javi's shown today. So yeah, join us then. Join us on the stream. Say hi. And yeah, thanks, Javi. Thanks so much for doing this.
No worries. Thank you. Thank you, Theo.